This is lecture 8. So let's continue our discussion on transmission line and the effect of long lines on distributed systems, right? So we were considering the case of where we have a transmission line and we had an input and this was open circuited, and we saw that if I look at the voltage waveform at this node, even though it seems like an open circuited transmission line, you can have periodic nulls, right? You can have periodic zeros at different frequencies based on whether for the corresponding frequency the length of the line behaves like the round trip delay through the line is a odd multiple of half time period, right? So if that is the case, then we can have destructive interference between the wavefront that is going in one direction and the one that is coming back, and at that juncture you can have a null. Now note that destructive, depending upon where you are observing it on the line, a destructive interference can happen anywhere in the line, right? It need not necessarily be at the input port. It can happen at different parts of the line. But if we are interested in only at the input point that we were discussing in the previous lecture, then obviously the length of the line has to have a certain specific relation with respect to the frequency of input, and that relationship is essentially that of a quarter wave transmission line, as some of you might be aware of it. Okay, so now in this lecture, what we would like to focus on is what happens if, let's say, if it's not open circuited. Let's say I have a transmission line and I have this is terminated with an impedance, or let's keep it simple and I say that is terminated with the resistance RL. The impedance of the characteristics impedance of the transmission line is Z0, right? And I am interested to find out what is happening if I terminate this line with an RL. Well, RL is not necessarily equal to Z0. Okay, fine. So how should we proceed? Let's assume, like before, that I have a forward going wave that is V plus, and this we are doing at the load end. Okay, and I have a reflected wave which is V minus. Okay, so what is the voltage at the output? V naught is nothing but V plus V minus, right? What about the current? What is the forward going current? What is I plus? I plus is nothing but V plus by Z plus. What is I minus? I minus is again V superscript negative by Z naught, right? So what is the net I that is going into the load? So I should say I naught. So this is I naught. Net I is I plus minus I minus. And what is I naught? I naught is nothing but the Ohm's law imposes this constraint. I naught is V naught over RL, which is equal to V plus over Z naught. minus V minus over Z naught, right? So which essentially means that your Z naught over RL and V naught is V plus minus V minus. Now if I take this equation and this equation into account, what do I get? I essentially get, if I subtract these two, so I get 2V minus is equal to V naught 1 minus Z naught over RL, right? And if I add these two, what I get? I get 2V plus is equal to V naught 1 plus Z naught over RL. So what is the relationship between V minus and V plus? So therefore, V minus over V plus becomes essentially RL minus Z naught by RL Z naught. And this relationship is, what is this relationship telling us? This is essentially telling us that if RL is equal to infinite, that is the case that we solved yesterday in the previous lecture. If RL is equal to infinite, then naturally V minus becomes exactly equal to V plus, that is the forward going wave and the reflected wave are identical. If RL is a short circuit, if RL equal to 0, then V minus is the opposite of, has the same magnitude but the opposite phase of V plus, right? And if RL is exactly equal to Z naught, then V minus is essentially 0, right? What does V minus 0 means? Means that there is no reflection at all, right? So what are the conclusions from this? So by the way, there is a term for this. This is often called reflection coefficient. Not often, it's always called reflection coefficient. So V minus over V plus is basically denoted as capital gamma. This is the reflection coefficient at any interface, right? Which is essentially equal to RL minus Z naught by RL plus Z naught. And the key takeaway from this is for RL equal to infinity, i.e. open circuit, your gamma is equal to plus 1, which means that V minus, this is a reflected wave, is equal to the wave that is incident on that open circuit port. If RL is equal to 0, i.e. short circuit, then gamma is equal to negative 1, which means V minus is equal to negative of V plus, right? Which means that your reflected wave has the same magnitude but opposite in phase, right? Whatever goes gets flipped. And most importantly, if RL is equal to R, this is often called the matched load. Right? Then gamma is equal to 0, then V minus is equal to 0. Right? So the key takeaway again is, if you do not want any reflection, then RL exactly has to be equal to Z naught. Now I showed this with RL. You can obviously do it for any complex load also. So in general, this should be ZL. This should be ZL. So for a for a matched load, ZL has to be equal to, I should not use R, right, because I have used Z naught. For the characteristics impedance. So for a matched load, your whatever your termination of your transmission line sees should be equal to Z naught. And why is this important? This is important because if I take you back to the previous lecture, the whole problem of the whole issue of signal going to zero at some point of the transmission line was happening because there was a reflected wave. If there were no reflections, then that problem wouldn't have appeared at all, right? So because the whole problem is that of a reflected wave, maybe in some applications we would like to get rid of the reflected wave through and through, and this gives us a framework of getting rid of the reflected wave all the time. Okay, so now before going forward, let me give you an example, or rather let me try to motivate why this is a problem in an antenna and an LNA interface. Okay, so let's try to look at it, right? So we have an antenna and you have a long transmission line, and the antenna, again, just like before, we will model it as some source and some resistance R, and you have a long line, and maybe we have a amplifier. Okay, this is a long line. Z naught and tau. Tau is the time delay. Okay. So let me start off with an example which is not a real life example, but it will give you an intuition as to why this can be a problem. So let's say I have a situation where I am sending instead of sending sinusoids, I am sending bits, right? So let's say I send a step in the first place. Okay. So and further I assume that Z naught is not equal to R, right? So further I assume that Z naught is not equal to R. So I will Z naught is not equal to R, and there is a time delay tau associated with the wavefront moving. Okay, so what's going to happen? Intuitively, first let's try to figure out what's going to happen, then we will try to do some math with respect to another example. So what's going to happen here? The first thing that is going to happen is at this interface, right? At this interface you are going to see some reflection, but that reflection is probably not much of an issue because we have assumed that the R is a lumped element which does not have any delay associated with it, but there will be some wavefront that is going to go forward. Okay, so essentially you are not going to see any reflection, but you are going to see some wavefront that is going forward. Okay, so now so this wavefront is essentially the step that moves forward after time tau. So this is, I would say, this is a step. What is the height of the step? We have not yet established, but it's a step that moves forward. So after time tau, this step reaches this junction. So it is still a step, right, of the same height that is at the other end of the line, but delayed by a time tau. But now it sees, let's say it's an open circuited interface, right? I do not know what the impedance is. Maybe LNA has some impedance. Some part of the waveform goes in, some part comes out, even if it's not open circuited. So there is a reflection. So there will be some reflection, and this reflection is going to travel. and after some additional time tau, this is going to come here. Okay, so far so good, but now here at this junction it is going to see a mismatched interface because Z0 is not equal to R. Because it is going to see a mismatched interface, this waveform is going to get reflected again, and it is going to get reflected again, and it is going to go back to the LNA interface, LNA transmission line interface, right? So again, so basically you are probably going to, depending upon what is the relationship between R and Z0, maybe it is going to be in phase or out of phase, I don't know. You are going to get some attenuated version of the step. Okay. So, and this will obviously keep on going for infinite time. So effectively, what you are going to see, if you observe the waveform here, if you observe the total waveform here, right, you are probably going to see something like a step, then maybe a small step, maybe it goes down, maybe it goes up, something like that, and eventually it is going to settle. Right, so this is an exaggerated version. It's not like your time, the length of the line will be like kilometers long, but you get the idea of what might end up happening, right? So eventually, it is going to reach wherever it's supposed to reach. But assume that the input is not a step, but the input is, let's say, a pulse or a set of pulses that you are trying to send. Then what's going to happen? All these pulses are going to have a response similar to that, whatever I showed you similar to this, and they are going to interfere with each other, and you are going to have problems because effectively whatever the LNAs will be seeing or whatever the amplifier will be seeing will not be the pristine input that it was supposed to see, but it will be a distorted input, right? So because what is the source of the distortion? The source of the distortion is we are seeing reflections at all the mismatched interfaces, and because you have reflections at all the mismatched interfaces, and not only reflections but reflections plus delay, right? Reflections are okay as long as there are no delays, but if there are reflections and there are delays, then you are going to see you are kind of going to see a very slow settling, and because of that you are going to get some you are going to get, in this context, intersymbol interference. Okay, uh, so in the context of sinusoidal waveforms, when you have a modulated sinusoidal waveforms, you can have similar issues. Okay, so if that is the case, then we'd like to ensure that given the fact that the strength of the input signal that we get from the antenna can already be very low, right, of the order of minus 100 dBm or so, we do not want to see any more attenuation, or we do not want to see any more uncertainty in the reception of the signal, just because there are reflections and delays associated with the interface. Okay, so that is so what is the fix? The fix is, again, if I am harping on it for since the start of this lecture, the problem is reflection plus delay. You cannot get rid of the delay. That's the setup, right? You have an antenna somewhere and you have a chip somewhere. Unless you put the antenna inside the chip, you cannot get rid of the delay. So if the delay is there, all you can do is to ensure that the reflection is not there, right? So how do you ensure the reflection is not there? You ensure that every interface that your system sees from the antenna to the input of the LNA has the same characteristic impedance, right? So essentially, what is the key takeaway? Ensure to prevent unwanted or to prevent uncertainty in the reception of signal, ensure every interface between the antenna and the input of the chip has the same characteristics impedance, right? So, i.e., this is often called design for reflection match. Okay, and this is something that you are not going to see in this is a problem that you are not going to see in analog circuits, typical analog circuits. uh, there are two reasons behind that. One is typical analog circuits work at much lower frequency than gigahertz and multi gigahertz. They typically are, as of today, and they typically work on sub gigahertz, few hundreds of megahertz at max, right? But more importantly, they normally the entire analog circuit, even if they work at multi gigahertz, they sit inside the chip, right? Because they sit inside the chip, the dimensions are much smaller than the length of the wave, or the wavelength of, they are much smaller than the wavelength. And if they are much smaller than the wavelength, then you don't really care about reflections, because the reflected wave and the incident wave will almost have the same phase, right? So if the reflected and the incident wave almost have the same phase, then it's not a problem. It's the analogy is, uh, when you are sitting inside a home, in the four walls of your home, and you are talking, you do not hear the echo of your sound that bounces back from the walls. But if you may shout at the top of your voice, you will not be able to hear any echo or discern any echo, but the echo is there. But if you go to a hill station and you are in a big space where there are interfaces, or there are places from which the sound reflections can happen, but they are located at a distance from you, like in the mountains and in the hills, and you shout at the top of your voice, you can distinctly hear an echo, right? So this is an echo problem. It exists everywhere, just that if the reflected wave is sitting on top of this, almost sitting on top of the incident wave, the effect of the echo is not visible. In this case, if the phase difference between the reflected and the incident wave is virtually zero, then it's not a problem. But if the length of the line is big, then that is not possible. And if the frequency of the waveform is large, that is not possible. So you'll have to deal with echo, or rather, you have to deal uh, uh, with the case, as in there should not be any reflection. In acoustic terms, this is often in acoustic examples, you will see that in very good theaters, which have to be really big, right, which can house a lot of people, you need to have special paddings which can absorb the sound and do not allow echo to happen. But you don't need such engineering when you are sitting inside your room, right? Okay. So before going forward, let me try and give you an intuition, a mathematical intuition, as to what happens if you have transmission lines in regular circuits, right? For example, let's take the example of a simple resistive divider. The voltage divider as we know it, let's say this is Vi, there is R, and let's say there is a transmission line having a characteristic impedance equal to R, and there is a time delay tau associated with it, and this line is terminated with R1, right? So that's the model of the transmission line that we have. By the way, uh, I probably have not stressed on this before, but before a slight digression. But what you should keep in mind always is that a transmission line is essentially a set of LC, right? So the return path, if it's a coaxial cable, generally, so the return path is the body. Okay. So when I draw a transmission line like this, it does not mean that the current going in, that is I, is the same as the current coming out. So I1, this is I2. It does not mean this, right? I1 is need not necessarily be the same as I2. Okay. It should be, I mean, moment you move your focus from a piece of line to an LC, to an LC tag, right? It will become intuitive because it will become explicit because this I1 and this I2 need not necessarily be the same, right? So that is something we should always keep in mind. Okay. Okay, great. So that was a slight amount of digression, but let's move our focus to whatever we have now. So what I would like to see is what happens to what happens to the voltage waveforms at this node and at this node, right? As time progresses and as we launch the waveform from Vi. Okay, so let's start. So what is our modus operandi? So I will assume that there is a forward going wave V plus, right? And there is a reflected wave V minus, right, at any time, right, at this interface. Now note that at this interface, what is reflection coefficient? Gamma. So at x equal to 0, gamma is essentially 0 because Z0 is equal to R. Okay. So if gamma is equal to 0, which means V minus is equal to 0, right? Which means I minus is equal to 0, correct? So I can basically get rid of this guy, and I know that the current that flows through I plus is nothing but V plus over Z0, correct? So what is the total voltage? Let me call this V1. The total voltage at V1 is equal to V plus. But if I want to express V plus in terms of Vi, what should I do? I need to have another condition, and that condition comes from the current, because the total current coming out of V1 is equal to V plus by Z0, right? But now I know that V plus, this node voltage, is basically Vi minus the current times R, correct? So I know that now I am imposing KVL. I can impose KVL here because R is essentially a lumped element, right? There is no time delay associated with it. That's the assumption. So since R is a lumped element, we can ignore effect of delay through R. So therefore, EI minus IR, IR is basically V plus by Z0, should be equal to V plus, sorry, V plus by Z naught times R. So, right. And since R is exactly equal to Z naught, right, where is that? V plus is equal to Vi over 2, since R is equal to Z. Okay. So what is this essentially telling us? The forward going wave is essentially Vi over 2. Okay, and there is no reflected wave, right? So what is the conclusion? So let me redraw the network here. So I know that this forward going wave is Vi over 2. Forward going current wave also will be Vi over 2 Z naught, and there is no reflection, no reflected wave. Okay. So this goes through, and after Vi over, after a time tau, right? So this wave front after time tau reaches this end, right? So this is x equal to 0, x equal to L. Okay. So basically it becomes Vi over 2, but after time delay of tau, right? So if I impose this condition, I mean assume that Vi is in time domain and it's a function of t. Okay. So what's going to happen now? What's going to happen at this junction? So at x equal to L, my reflection coefficient gamma is not 0, right? That is R1 minus R by R1 plus R. Okay. So which essentially means that there will be a reflection. I will call it P minus at L should be is equal to gamma. I should also write gamma at L, gamma at L. Ideally, the convention is to write this gamma to be at the source and gamma to be at the L, to be at the load side as gamma L. So this is V minus times gamma L times Vi over 2 T minus tau, correct? Okay. So we are going to have a, what will be the total output voltage then? So therefore V naught at time t equal to tau, or I did not write it since I am expressing it in terms of I have kept it generic. I can also keep this generic. So V naught should be equal to 1 plus gamma L times V plus, that is Vi by 2 times tau, right? So what is 1 plus gamma L? 1 plus gamma L is nothing but 2 R1 by R1 plus R times Vi by 2 T minus tau, which means that your V naught is nothing but Vi R1 by R1 plus R times the delayed version of Vi T minus tau. Okay. So this is the output, right? And since I am only considering one reflection, this is I should write as after one reflection. Okay, fine. So now the story doesn't end here. because there is a reflection that has happened at this interface. There is a V minus. So a V minus also flows through. The V minus is essentially gamma L times Vi by 2 T minus tau, and after an additional time duration of tau, that is at after 2 tau from the time it has launched, it is going to reach to x equal to 0, right? So once it reaches x equal to 0, so this will be gamma L Vi by 2 T minus 2 tau, right? But now note that it has come to a matched interface again, because the direction of the wave is going into R, right? And it is coming through a transmission line having the characteristic impedance R, which means there is no further reflection, right? So which essentially means that it goes through, and if it goes through and there is no further reflection, what will be the voltage that it will accrue at that interface? The total voltage that is going to accrue at the interface. So since there is no reflection, there is no reflection at x equal to 0, therefore V1 will be equal to Vi T plus gamma L times Vi by 2 T minus tau, right? Vi by 2. Okay. So now, because there is no further reflection anywhere in the network, right? So this becomes the final V0, and this becomes the final V1, right? Because there is no further reflection. So now we have to make sense, do a sanity check to see whether this actually makes sense or not. So what is the sanity check? The sanity check is, let's assume this is a line where the length of the transmission line is close to 0, right? It's a very minuscule transmission line, right? So if the length of the transmission line is close to 0, then this circuit is essentially, I can assume it's a very small line, right? So this circuit reduces to the classical resistive voltage divider with R and R1, right? So which essentially means that your V0 is the same as V1, right? So if tau tends to 0, let's see whether this makes sense. If tau tends to 0, your V0 essentially becomes R1 by R1 plus R times Vi, right? So that's what it is supposed to be. But what is V1? So I am getting V0 is equal to R1 by R1 plus R Vi if tau is equal to 0, right? So this matches. But what about this guy? So V1 will be equal to Vi by 2 plus gamma L. Gamma L is R1 minus R by R1 plus R, and this will be VIT. This is also VIT, right? So this is again nothing but R1 by R1 plus R times VIT, right? So you see both the transmission line picture and the lumped element picture converge with the transmission line length goes to 0, right? So you can also do this. You can also verify this using simulation. So if you have access to any simulator, there are many free circuit simulators available, like LD-Spice, NG-Spice, and so on. If you are interested, you can download one of those simulators and set up the circuit like the one that you are seeing here, and you can basically put a transmission line of varying length and then see what happens at every point on the transmission line and how the signals converge to a lumped element approximation when when tau tends to 0, right? So that's a fun exercise to have, to go through, and I would encourage you to go through it if you have time, and if you can download some of those freely available tools. Okay. So before we stop, so the key takeaways are, so we saw, what did we see? We saw that with an example, not rigorously, but with an example, we saw that distributed or transmission line networks or response in a transmission line network converges to lumped element network when tau of the transmission line tends to 0, right? And number 2, we saw that if there is a mismatched interface, then there will be reflections but or however they might not be apparent if the delay of the line is much less than time period of the waveform. Okay. The third important thing that I have not mentioned explicitly, to eliminate matching, ensure ZL is equal to Z0. This is not the same as ZL is equal to Z0 star, right? Some of you probably from your UG days might have, I'm sure you have gone through this, that maximum power transfer theorems and so on. So maximum power transfer theorem, we know that for a given source impedance, right, the load impedance should be conjugately matched, complex conjugately matched. So that ensures maximum power transfer, but that does not ensure no reflection. So that's why this is called a reflection match, and that is called a power match, right? So in so far we have been in whatever we have been talking of till now is essentially reflection match. Strictly speaking, this is not a power match. Okay. The another interesting thing, that an extension to the problem that we solved here is you can invoke. Here I took a case where the transmission line is matched to R. That did not necessarily be the case. you can have this, you can do the same thing by assuming the transmission line is not matched to R but maybe matched to R1, right? So it's a good exercise to do. You can do it yourself, that assume the transmission line is matched to R1, uh, and then go ahead and do it. The trick, the hint to going ahead and doing it in the same way as I did right now is the fact, is to recognize the fact that the impedance. So if you have a line having Z1 and tau, and this is terminated with Z1, I know that there is no reflection anywhere in the line. So I know the forward going wave is the only wave, that is V plus, the voltage wave. The forward going current wave is also V plus over Z1, right? So what is the impedance? The impedance looking in is essentially total voltage by total current. So Z in is total voltage by total current, which is equal to Z1, right, regardless of how big the line is. So if that is the case, you can invoke, then you can basically say that if something is connected here with R, and you have something like this as Z1 and this is Z1 tau, if I know that the impedance looking in here is Z1, then I know the voltage here, right? The voltage here is essentially Vi Z1 by R plus Z1, which goes in, right? So Vi V plus is equal to, at this node is, if I call this V plus 1, so V plus 1 will be this, right? So you can use this and solve for it. Okay,